Next, we want to look at heat transfer and change of phase, two very important topics. Okay, the question we have is, how does heat flow from one body to another? Now remember, we talked last chapter about what heat is. Heat is not something that an object has intrinsically built in. Heat is the thermal energy that flows from one body to another body. Now, you can make it flow from a colder body to a higher temperature body by doing work on the system, but otherwise, heat is always going to flow from high temperature to low temperature. Spontaneous flow of heat will always be from high to low temperature. But how does it happen? That's the question that we want to ask and answer now. And it turns out there's actually three different ways that it can happen. The three different mechanisms by which heat can be transferred, can flow from one body to another, is conduction, convection, and radiation, specifically electromagnetic radiation. And these are the three main ways that heat will flow from one object to another. The first mechanism of heat transfer that we want to talk about is what we call thermal conduction. And it is the transfer of internal energy by microscopic collisions of particles and movement of electrons within a body. That sounds complicated, but it's really not. So let's talk about what that really means. Over here on the left, we have a bar of some material that's at a higher temperature. And over here, we have a bar of the same material or a different material, it doesn't matter, of a lower temperature. Now, we put these two bars of material at different temperatures together, so now there is a common surface where they're touching. And so the heat can conduct from the higher temperature to the lower temperature. But why does that happen? Well, think about it this way. What does it mean for there to be higher temperature? It means the average kinetic energy of the motion of the particles that make up that substance is higher. The things are moving faster. And so you can see here, I've got a particle that's moving, and it's got a big arrow because it's got a high velocity. It's going really, really high. It's hitting here, and then at the surface, it strikes some of the particles from the other material, and you can note that's a little green arrow, and that little green arrow means it's moving more slowly because lower temperature means things are moving slower. Now what happens is this high temperature, fast-moving particle strikes the slow-moving, low-temperature particle, and there's a change of momentum. So this guy gains some of the momentum and some of the energy of that guy. So what happens is this guy speeds up, and so you can see after they bounce off of one another, this guy's got a bigger arrow, it's going faster, and this guy slows down. So what we have is we have this fast-moving guy collides with this slow-moving guy, and they exchange momentum. And so this guy speeds up and is going faster, and this guy slows down, so he's going slower. So this guy lost some momentum, and this guy gains some momentum. Now we know because their velocities have changed, their energy, specifically their kinetic energy, has changed too. So this guy is now moving with a higher kinetic energy, so the temperature of this guy's just gone up a little bit. The temperature of this guy's gone down a little bit. And this will continue happening, more and more collisions over and over and over until they come to a common temperature. And so this higher temperature, these guys are moving faster, they've got more energy, but they collide with the slow-moving guys over here, and the energy gets transferred. The heat, we say, flows from this guy to that guy. Here we can see some examples of the flow of heat happening through the process of conduction. So figure 7.1, you have this guy, he is standing on a floor, but here's a wooden part of the floor and here's the tile, so maybe this is his living room, it's got a hardwood floor, and this is his kitchen, which is tiled. And you may have experienced this yourself. You step on the tile, it feels colder. But what's weird about this, if you were to put a thermometer here and a thermometer there, the thermometers would read the same temperature. This guy's not actually at a lower temperature, it just feels that way. So why? It's because the tile is a better conductor of heat than the wood. And so what happens is your foot is at a higher temperature, so the heat flows out of your foot into the tile, And so your foot's kind of losing heat. And that means your foot feels colder on the tile than it does on the wood. It's because of that conduction of heat. So the thing to take away from that is that some things are better conductors of heat than other things. Later on, we're going to talk about electricity, and we'll find that, generally speaking, things that are good conductors of heat are also good conductors of electricity, and vice versa. Now, here's a question in figure 7.2. We have a nail that's been driven into a block of ice, and so you're going to touch the nail. Which way does the heat flow? Does it flow from the ice into your hand and make your hand cold, or does it flow from your hand into the nail and into the ice and make the ice warmer? The answer is the latter. The heat is actually flowing from your hand into the nail and into the ice, but your finger feels colder because you're losing heat when this happens. The heat's flowing out of your body. Now, many of my students are too young to drink wine, I'm sure, but you may have noticed that very often wine glasses have long stems. If your wine is chilled, you don't want the heat from your hand to flow into it and warm it up too quickly. And so the stem is basically insulated away so that the heat flows into the stem, not into the part where the wine glass is holding the wine. So that minimizes the transfer of heat from your hand to the wine, so your wine stays cooler longer. Now, I've used a couple of words here, and I haven't really defined them, so I want to step back and make sure that we understand what these important words mean. So the first word that we want to look at is the word conductor. And let's go back to the example of the wood floor and the tile floor. I said that the tile was a better conductor of heat than the wood floor because the heat flows more readily into the tile from your foot than it does with the wood. And so things that allow heat to easily flow, we call conductors. So this is our key idea. If you have a conductor, the heat flows easily into that material or out of that material. Now, another thing I said was that the wine up here is insulated by the glass. And so an insulator is a material where the heat does not flow easily. And so these are two very important concepts. We have the concept of a conductor and the concept of an insulator. Okay, here's a couple of interesting questions we're going to use to kind of illustrate some of these ideas. The first question that we're looking at says, in the desert regions that are hot in the day and cold at night, the walls of the houses are often made of mud. Why is it important that the mud walls be thick? The answer is that mud is an insulator. Now, if you imagine a wall that has a certain thickness, and if it's hot here and it's cold there, the heat is going to flow through that wall. But the insulator makes it harder for the heat to flow. It kind of slows it down. And so if the wall is thicker, that means that the transfer of heat is going to take a longer time. So imagine that you have a hut and it's hot out during the day, and it's cool inside because, in the morning it's cool and it gets warmer and warmer outside. Well, the heat's going to flow into your hut and it's going to warm it up. But if you have nice thick walls, that's going to slow down that heat. Now, on the other side, when it gets night and it cools off, so now it's warmer inside the house and it's cool outside, well, you don't want to be too cool, but the same process is going to apply. The warmth, the heat's going to flow outside to the cooler outside of the house, but it's going to slow it down. So your house will stay cooler longer during the day, and it will stay warmer longer during the night. And of course, if you have not some kind of hut, but a house, you're still going to have an air conditioning system or maybe some kind of heating system, and that's going to reduce your bills if you have better insulating walls. The better the insulation of the walls is, the slower the heat's going to flow out of them or into them. And so that's why the thicker walls are better, because they make better insulators. Now the next question says, wood is a better insulator than glass. That is, if you have a block of wood and you have a block of glass, the wood is going to be better at insulating than glass would be. Yet, we don't insulate our houses with wood. We generally use fiberglass. Why? Well, if you don't know what fiberglass is, that would make this kind of a hard question to answer. But fiberglass is literally what it sounds like. It's a bunch of glass fibers that are packed together. Now, the thing that makes fiberglass such a great insulator is that you have all these fibers packed together, but there's a lot of air in between the fibers. And it turns out that air is a really good insulator. And so that is the reason why fiberglass is better than solid wood as an insulator. Okay, so far we've been looking at conduction as a mechanism of heat transfer. The next thing that we want to talk about is what's called convection. Now, convection is the transfer of heat through mass motion due to density changes. And so imagine you have a pot of water and all the water is at the same temperature and you put it on the stove. And so you've got heat going into the pot from the bottom. And so the water kind of in the middle and at the bottom is going to heat up and become warmer. What happens to things when they get warmer? Well, their temperature goes up and they expand. And so they warm up and they expand. And as they expand, they become less dense. And so the cold water up above is going to flow down to replace. And so the warm water is going to rise, and then the cooler, more dense water up above is going to fall down to replace it. And so now the cool water is at the bottom being heated, and the warm water is at the top cooling off a bit. But again, that same process is happening. And so the cool water at the bottom is warming up and it's rising. The water that's colder at the top, it comes down. And so if this were just a block of metal or something, we know that this process would heat through conduction. And so the vibrating fast molecules here would be colliding with the slower moving molecules next to them, and the collisions would transfer the heat energy, and the heat would flow upwards through the process of conduction. But here, because the water is able to become more dense or less dense as it's heated up, you can actually get mass motion flowing through the water. That is, the water rises and falls, and that transfers the heat because the warmer water is rising and moving over here, the cooler water is coming down and being heated up, and so that aids in the distribution of heat. So the heat is flowing through the water, not just by conduction, but also through this process of convection. Now here's actually kind of an interesting application of this process of convection. And so you can see there's some guy, he's built a campfire here, he's got a tent, he's camping by a big lake. And let's say the sunlight is coming down and it's warming the water and it's warming the ground. We know that water has a really big specific heat. And so it takes a lot of heat to warm that water up, so it might be at a little bit cooler temperature than the land. And so that's going to create sort of a conduction effect. The warmer land is going to drive the air up, and the cooler water here, as the warm air rises, it's going to sink down over here, and that creates a cycle of current. So the wind is coming from the lake onto the land. But at night, the reverse happens. So remember, water has a really big specific heat. That means not only does it take a lot of energy for it to heat up, it also takes a lot of energy change for it to cool down. So it's not going to cool down as quickly as the ground. And so when the temperature at night falls, over here it might be 60 degrees, over here it might be 64 degrees. And so you're going to get the warmer air over here is going to rise and the cooler air over here is going to fall. And that causes the wind to flow out to sea or out over the lake instead of from the lake. And that's sort of understandable by understanding how this process of convection works. The next thing that we want to look at, the next topic that we want to look at, is electromagnetic radiation. Now that is, of course, the third mechanism for heat transfer. Everything that has temperature, that includes the chair you're sitting in, you, the planet Earth, the moon, the sun, everything that has temperature is radiating electromagnetic radiation. Now the sun, it so happens, is at such a high temperature, it radiates a portion of the electromagnetic spectrum that we call visible light. That's why you can see the light coming off the sun. You and I, we're much lower temperature, and so we don't radiate visible light, we actually radiate what's called infrared light. You might have heard of infrared light before. But basically, we are all emitting electromagnetic radiation. Now, the higher the temperature that something is, the higher the energy and frequency of the electromagnetic waves that it gives off are. So that's why I give off infrared light and the sun gives off different visible light, because the sun is at a higher temperature, it gives off light that corresponds to that temperature. Now, I'm sure that most of you, probably all of you, learned about electromagnetic waves in grade school. So this should be something that you're hopefully a little bit familiar with. We know there's a whole spectrum of waves, of electromagnetic waves, that go from radio waves to infrared to visible light. And if you went further over here, you'd have ultraviolet and X-rays. But the key thing is that these waves, what makes them different is how quickly they're vibrating. And so here you can see sort of a young girl here. She's got a rope tied to the wall, and she's shaking it up and down to send waves down the rope to the wall. And if she shakes it up and down faster, there'll be more waves traveling to the wall. And so here she's shaking it kind of slow, so you get a couple of waves. Here she's shaking it faster. You get a higher frequency of waves is what we call that. More waves per unit time. Now, since there are more waves here when she's shaking it faster, each wave is shorter. So we say the length of the wave goes from where you start to repeating the wave. So it goes up and down and then back, and so that's where it starts again. Then it goes up and down and back, and that's where it starts again. So from here all the way to there, that would be one length of the wave. Now up here where the waves are going slower, you can see that that process is longer. So I go here, up, down, back to where I started. That's a much longer wave. And so we call the length of the wavelength. That makes sense, hopefully. And the basic rule of thumb is the bigger the frequency, the more shakes you have, the shorter the wavelength. So bigger frequency means shorter wavelength. And up here we have a smaller wavelength. We have a smaller frequency, less shaking, and that gives rise to a bigger wavelength, a longer wave. Now, the frequency and the wavelength, they actually depend on what temperature you are. And so something cool is going to give off a low frequency, long wavelength radiation. Something of meteor temperature is going to give something a little bit shorter wavelength and higher frequency. And then something hot is going to give you a much higher frequency and a much shorter wavelength. And so the frequency of the wave actually is also what corresponds to the color. Whether the light is blue or green or red, it depends on how fast the vibrating charges that created it are shaking. Now, when we say color, most people think of the colors of the spectrum: red, green, orange. You know all the colors, right? But they're also infrared, radio waves. Over here would be ultraviolet. We could consider those colors as well, because the only thing that separates infrared waves from visible light waves is the frequency of the radiation. Now, here you can see a sort of a listing of the electromagnetic spectrum from all of its regions. So up here we've got radio waves, microwaves, infrared, visible, ultraviolet, X-rays, and gamma rays. And so the wavelength is longer at the radio end and shortest at the gamma ray end. And down below the waves, you can see sort of something for scale, that at these wavelengths, so this is a wavelength of 10 to the third meters, that's 1,000 meters, that's how long the wave is. That goes down. Now, as you're increasing the frequency, the shaking is getting faster and faster, the wavelength gets shorter. So we go from 10 to the third to 10 to the minus 2, and we call that part microwaves. It's still part of the radio portion of the spectrum, but we call that region microwaves. That's why your microwave oven is called a microwave oven. It uses that portion of the spectrum. You can see that you're getting down to the wavelength being about the size of a honeybee. Infrared, about the size of a pinpoint. Visible, different kinds of bacteria. Ultraviolet, you're getting down to the size of molecules. And then for X-rays, the wavelengths are so short, they're about the size of atoms. And gamma rays are so short, they're about the size of the nucleus of the atoms. So you can kind of see that. And here we see the wavelengths. Now, here we see the frequency. Again, here we have a big wavelength, 10 to the third, and 10 to the fourth sounds like a pretty big frequency, but it's actually not, because as we go over to the right, we can see 10 to the 6, 10 to the 12, all the way up to 10 to the 20. And so as these numbers are getting smaller and smaller, the wavelengths are getting shorter, the frequencies are getting bigger and bigger and bigger. Now, I said everything that has temperature is radiating electromagnetic radiation. This is showing you the sort of temperatures, how hot you need to be able to emit those different colors. So something about a Kelvin is going to be emitting microwaves. Something about 100 Kelvin is going to be radiating infrared. Something about 10,000 Kelvin is going to be up in towards the visible, and then millions of Kelvin, you're getting up to the ultraviolet, the X-rays, and even the gamma rays.